So today's lecture is going to be about limiting reactants. You actually do this every single day in your life. You just call it something different. So with limiting reactants, if you've ever been or held a barbecue and you had to get hot dogs and hot dog buns for your guests, you kind of play this mathematical game where you're trying to buy the correct number of hot dogs, which come in packages of 10, with the correct amount of hot dog buns, which come in packages of 8. It's not an even number. So you do that game in the grocery store where you're like, okay, I have 20 people coming, so I need at least 2 packages of hot dogs and 3 packages of buns, but then I'm going to have leftover buns, so maybe I should buy some more hot dogs, maybe people want more than one, etc. You do this in your life every day. You just call it something different. If we look at this pizza scenario here, one of the things we can think about is how to think about what a limiting reactant is. So if my ingredients say that a pizza is made of 1 crust, 5 ounces of tomato sauce, and 2 cups of cheese, that'll give me 1 pizza. If I look at each individual set of ingredients, assuming everything else has as much as my little heart could possibly desire, then I can figure out how many pizzas I could make all in all. So if I look at just the crusts, if I had all the cheese in the world and all the tomato sauce in the world, because I only have 4 crusts, I can make 4 pizzas. Now, if I consider my cheese, it's 2 cups of cheese per pizza. So if I have all the crusts in all the world and all the sauce in all the world, I can only make 5 pizzas. 2, 4, 6, 8, 10 cups is what I have total. Finally, if I look at just the sauce and say, okay, I have 15 ounces of tomato sauce, I have all the cheese I need, all the pizza I need, but each pizza needs 5 ounces of sauce. So 15 divided by 3, I said 5 equals 3 pizzas. Okay, so the most I could make is 3 pizzas. So in this pizza scenario, the limiting reactant or the limiting ingredient to make my pizzas is the 15 ounces of tomato sauce I have. So it doesn't really matter that I have 4 crusts or that I have 10 cups of cheese. I only have 15 ounces of the sauce, so I can only make 3 pizzas. What this also means is that if all of this is used up, then what I'm going to have is 2, 4, 6 cups of cheese used with 4 cups left over, and then 3 crusts used with 1 crust left over. So I can say to myself, how much did I use of each ingredient to get my final 3 pizzas, and therefore how much is left over? This is what we're going to be doing with reactants. We're going to be looking at each reactant and we're going to see how much we could possibly get as a product. And then we're going to determine which one limits us. The one that limits us is the one that gives us the least amount of product. So let's just work this doing an example. Here's an example. Ammonia and H3 can be synthesized by the reaction here. This is our reaction. We know our starting materials are 86.3 grams of nitrogen monoxide and 25.6 grams of hydrogen gas. This is our starting material. So you know this is a limiting reactant problem for 2 reasons. The first reason is it gives you the grams for each reactant, and it's asking you for a theoretical yield. Those are the 2 reasons that you know this is a limiting reactant problem. One of those is going to limit the amount of ammonia that I can get in grams. Keep in mind, theoretical yield means theoretically on a piece of paper in a perfect world in a vacuum. I don't spill anything, I measure perfectly correctly, the reaction goes to 100% completion. Theoretically, mathematically on a piece of paper, how much ammonia can I get? Okay, now actually, your theoretical versus actual is going to be your percent yield, and we're going to talk about that too. So actual, meaning I go into the lab, I do this experiment. How much do I weigh out of ammonia in the end in the lab doing it? Over theoretical times 100% is our percent yield. Now, if you remember from last lecture, this is a mass-to-mass stoichiometric problem. We are given masses, and it's asking for a mass. So this is a mass-to-mass. If you remember and recall, we're going to be going from grams of the given to moles of the given to moles of what's asked for, because that's how I can relate it. How do I get to moles? And then back to grams of the asked for. Now, our relationships, we're going to have the molar mass of nitrogen monoxide, hydrogen gas, the mole-to-mole relationship between the nitrogen monoxide and the ammonia, and then the mole-to-mole relationship between the hydrogen gas and the ammonia, and then the molar mass of ammonia. So how we're going to go ahead and solve this is pretty simple. What we have to do is just do the math. And what that means is we're going to take each reactant and convert it from grams to moles, moles to moles, and then back to grams. So we're going to have 86.3 grams of nitrogen monoxide. I'm going to just quickly look back and see what my molar mass is. It's 30.01. And then I'm going to compare my mole to mole of the nitrogen monoxide to the ammonia. I don't know where my arrow went, so I'll do a little arrow there, sorry. And that's just a 2-to-2 ratio. Okay, and I'm going to stop at moles. It saves me a step, and then I can figure out by moles which one is going to give us the least amount of product, and whatever that one is, I'll convert to grams of ammonia. So I'm going to say 86.3 times 2 whole thing divided by 30.01 times 2, and I get 2.875 moles. Okay, now I'm going to do the exact same thing with the hydrogen gas. Hydrogen gas, molar mass is 2.02. I just added together 2 hydrogens. And then its relationship is 5-to-2. So 5 moles of H2 to 2 moles of NH3. I'm going to do that math. So it's 25.6 times 2, whole thing divided by 2.02 times 5. And that gives me 5.069 moles. Now, what this means is if I had all the hydrogen gas in the universe in excess, remember we had a problem like that, and I only had 86.3 grams of nitrogen monoxide, the most ammonia I could make is 2.875 moles of ammonia. Now, if I had all the nitrogen monoxide in the universe in excess, as much as I could possibly need, but still only had 25.6 grams of hydrogen gas, then I could make 5.069 moles of the ammonia. Well, in this case, it is the nitrogen monoxide that limits us. I don't have excess of hydrogen gas. I have 25.6 grams. So the nitrogen monoxide is going to be our limiting reactant, and that means the hydrogen gas is going to be what's in excess or left, or we're going to have some left over. So now that I know how many moles I could possibly get, I'm going to go ahead and now convert this to grams. And I'm going to convert it to grams because that's what it asks us for. This is a mass-to-mass problem. So my molar mass is 17.03. So I'm going to take 2.8757, divide it by, or I'm sorry, multiply it by 17.03, and I get 48.97 grams. Okay. Now, if we're paying attention to significant digits, then my final answer can only have 3 sig figs. So we're going to say 1, 2, 3. 7 is greater than 5, so we're going to round up. We're going to say 49.0 grams. So our limiting reactant, again, oh, I missed a, no, I didn't. Okay, sorry, I'm getting myself a little bit confused. Final product, that's the most I can get. Now, here's another one. We can obtain titanium metal from its oxide according to the following balanced equation. Here it is. And they're telling you it's already balanced for you. But one of the things you need to do is always check. It takes 2 seconds. Just check and make sure it's balanced, because sometimes you will not get a balanced chemical reaction. They won't give it to you. You have to balance it first. So always check. We have 28.6 grams of carbon, and it reacts with 88.2 grams of titanium 4 oxide. When that happens, we get 42.8 grams of titanium produced. Find the limiting reactant, the theoretical yield, percent yield, and the amount of excess left over. So here, they're not telling us what the limiting reactant is, but they are telling us how much product will be produced. That's going to matter because this is going to be the actual. Somebody went into a lab and did this reaction, and they actually produced 42.8 grams. All right. So to find our theoretical yield, we have to find the limiting reactant. Finding the limiting reactant tells us our theoretical yield. On a piece of paper, mathematically, in a perfect world, what should we have gotten for product? Okay, so I'm going to do the exact same thing I just did. I'm going to say 28.6 grams of carbon, and I'm going to convert that to moles. Then I'm going to use my balanced chemical equation to convert between moles of carbon and moles of titanium, because when I use those coefficients, I can relate the two as far as their ratios. Then I'm going to just stop here, just to remember, we're going to stop at moles just to make it one step easy. And then whatever our final lowest amount is, we'll convert those moles to titanium grams. So 28.6 divided by 12.011 multiplied by 2, and I get 1.19 moles of titanium. I just want to mention something really quickly, in case you were wondering this. You can see from our previous example that just because something is in a greater amount of starting material, this is a bigger amount than this, does not necessarily mean the larger amount is going to be the one that is in excess, and the smaller amount of stuff is going to be the limiting reactant. You can clearly see from this example that the amount that had the greatest starting amount, the nitrogen monoxide, that was our limiting reactant. So don't just look and say, oh, 28.6 grams of carbon and 88.2 grams of titanium 4 oxide. Oh, that must be our limiting reactant. because, the carbon must be because it's in the least amount. That's not necessarily true, so you can't rely on that, okay? All right, so now I'm going to do the same thing. Oops. Let's see, 88.2 grams of titanium 4 oxide. I'm just going to quickly add the molar mass of that up by just looking at my periodic table and saying 47.90 plus 15.9954 plus 15.9954, and that is a molar mass of 79.8908 grams. Now I'm going to do my mole to mole ratio that I get right from the balanced chemical reaction. It is a 1-to-1. Now I'm going to do the math. 88.2 divided by parentheses 79.8908 close parentheses, and I get 1.10 moles of titanium. Now in this case, the one that gives us the least amount is the 88.2 grams of titanium 4 oxide. So it is the titanium 4 oxide that is our limiting reagent, and the carbon is the one that's going to have excess or be left over or have leftovers. Okay. So now I'm going to go ahead and take my least amount here and convert that to grams. The molar mass of titanium is 47.90. I get that right from the periodic table. So that times 47.90, and I get 52.88193 grams of titanium. So our limiting reactant in this case is the titanium 4 oxide. And our theoretical yield, we found it is 52.9 grams. With our correct sig figs, these are our answering the limiting reactant and the theoretical yield. Now our percent yield is actual over theoretical times 100%. If we go and look, we can see that the actual is 42.8 and our theoretical is 52.9. The 42.8. No, that's 42.8. And then 52.8 grams. So we have our actual, what somebody did in a lab, actually doing in a lab, and our theoretical. On a piece of paper, mathematically, in a perfect world, what should they have gotten? And this is times 100%. So I'm going to go ahead and calculate that. 42.8 divided by second answer times 100%. And that equals 80.9350%. So to maintain our sig figs, it's just going to be 80.9%. And that's it. That's the easiest part of this, actual over theoretical. Now, To find the amount that was in excess, think about going back to the pizza example. We knew the tomato sauce was what limited us. So based on how much tomato sauce we had, we could only make 3 pizzas. How much cheese did I have to use to get those 3 pizzas? 2, 4, 6 cups. We started off with 10 cups. So we had 4 cups of cheese left over. In our example, we have to figure out how much of the carbon had to get used. How much of that 28.6 grams of carbon was used in order to get the 52.9 grams of titanium. So what we're going to do here is work backwards. It was 52.9. Okay. So if I had 52.9 grams of titanium used, we have to convert that back to grams of carbon, because that'll tell us how much of the carbon was used. Of the amount we started with, how much of that was used. So 52.9 grams of titanium was made. I'm going to convert that back to moles. So it's 47.90 grams of titanium to 1 mole of titanium. I need to go back and look at my reaction, my bounce reaction, to see that it's 2-to-1 ratio. So it was 2 moles of carbon to 1 mole of titanium. And then I'm going to convert carbon back to grams. And I'll just do the math really quickly. 52.9 times 2 times 12.011. Whole thing divided by parentheses, 47.90 times 1 times 1. And I get 26.5295 grams of carbon used. So 26.5295 grams of the carbon was used up to make that amount of titanium. Now, I started off with 28.6 grams. That's what I started with. I used 26.5295 grams. So the difference here between them is 2.07 grams left over. Now, what this means is, of the 28.6 grams of carbon that I started with, I had to use 26.5295 grams of it to make the titanium. And so that means I have 2.07 grams left over. So this is the amount in excess. It's left over. So first we had to find the limiting reactant. That told us how much of the product we were going to make. Then we had to figure out how much of the excess or the non-limiting reagent was used up to make the amount of product we had. Once we can figure that out, we just subtract it from the original, and that tells us how much is left over.